In this video, I'm continuing this class equation. Okay, some few things I wanted to note about the class equation. One is this fixed point theorem, and another one is normal, subgroup, and normalizer. Okay, let us recall the class equation. Recall class equation. R of G. Okay, in general, that class equation, let's say G acting on X. X can be written as G orbits. X is nothing but summation G orbits. Okay, now let's do the fixed point theorem. This is a class equation in general sense, and I used one particular action to prove that a particular class equation where X equal to G itself and acting as a conjugation action. Okay, now fixed point theorem. This you can see in the Michael Artin book. Let G be a P group. I'm doing this because of a Silos theorem. Later on Silos theorem, we use this. Okay, and G acts on X finite set. Okay, such that P does not divide order of this thing. Then there exists A belongs to X such that the conclusion is stabilizer of A is G itself. Let's prove this. So there exists a one element where G acts on trivially. That is what it means. Proof. It is very important to prove Silos theorem. Okay. Since X equal to G orbits and finite set, remember that X is finite, G orbit, P does not divide X, that implies there exists at least one orbit where let's say OA where P does not divide order of OA. If such orbit does not exist, if P divides all of the orbit, then eventually P should divide, because it's a summation, right? All of the orbit cardinality, then P should divide the cardinality of X. Okay, now I want that A. Let's say orbit stabilizer theorem. Using orbit stabilizer theorem, we get this: order of G equal to order of the orbit stabilizer. Sometimes I use Gx, sometimes this notation, both are same. Remember that G is a P group. P divides order of G. In fact, P power alpha divides order of G. That implies P power alpha divides step of A, orbit of A, but P does not divide orbit of A, so that implies P for alpha should divide stabilizer of A, and that says that stabilizer of A must be greater than or equal to P for alpha, but that is a subgroup of G, so that is less than or equal to P for alpha. That implies G must equal to stabilizer of A. So that implies for that particular A belongs to G, step of A equal to G itself. This is what fixed point theorem. That means G fixing this A. So what is the stabilizer? Let's call that stabilizer step of A, set of all G such that GA equal to A. In our case, G comma A equal to A for every G. So this is what fixed point, fixing. The entire G is fixing. That's why it's called fixed point theorem. Okay. And one more thing I wanted to add about normal subgroup and normalizer. Okay, normal subgroup. Okay, let G be a group, H is a subgroup of G, let H be the subgroup of G. We say H is normal in G if G H G inverse, that is equal to H is the variable here, equal to H itself for every G. Then we say that is normal. Okay, and the notation for that we use this normal. Okay, now normalizer of a group, subgroup. Let G be a group and H is a subgroup of G. So the normalizer of this is defined set of all G belongs. This is going to play a crucial role in the proving Silos theorem, especially third Silos theorem. So you have to give importance to this. Okay, H. So I'm collecting only those G inside the group which satisfies this condition. Okay, stepping. This is a subgroup. In fact, we can give a group action to prove this subgroup. So what is that group action? So G acting on subgroups. This is a collection. How? G subgroup is nothing but, you check, this is a group action. So let H belongs to that collection, which is subgroup collection, and the step of H is exactly the normalizer of H. And remember that H inside the step of H, and also H is normals to step of H. That's how we defined. Okay, remember that this is a condition, this is the condition, stabilizing condition. Okay, this is a condition, that's why I defined. So H is normal to this thing. So in other word, NH inside G is a largest subgroup of G where H is normal. We start with the H. Okay, NH is the largest subgroup of G where H is the normal. Okay, this is a small lemma I wanted to prove. All these explanations I gave, small lemma, which is easy to prove. I'm not going to prove, I'm going to prove. In fact, I'm just giving the idea. Let N be a normal subgroup of G. So first, then N is a union of conjugacy classes. Okay, second, final setup. Okay, final group. The order of N is sum of the order of the conjugacy classes. Okay, and okay, this is 3, actually this is 2. N is union of conjugacy classes. You have to see my all videos to understand this point. The point is very easy. The one is the proof. N is invariant set under the action Gx inverse, conjugacy class action. First G, I am acting on G by this. Okay, then N is normal. So n is a invariant subspace. N is normal to G, hence that is n is invariant. In the explanation notes, I have talked about in the examples what is invariant and a restriction operation. So G operates on n restrictively. This restriction happens because it's invariant. So we know that, right? G orbits. Whenever there is action, the order of n equal to summation of G orbits. So that's all this proves this thing. Okay, one stop. This is the idea. This proves all these things. Okay, now let G be a collection. What I'm going to do next one is okay, the theorem. This is also fairly simple. Let H be a subgroup of G, then n of H be, let n of H be its normalizer. One, this is more like summary. I proved already. H is normal to n of H. This is also I proved. I'm just summarizing. No. This is also I said. Anyway, I will summarize. Okay, so first thing is that this is I said already in the here. Okay, the second thing is I said the largest subgroup where this is normal. When H is a normal in G, that is the largest subgroup, so that is equal to this. When this is the largest subgroup equal to this thing where H is a normal, so that is also I explained. This is a resummarizing. This is Lagranges theorem. H is normal to NH subgroup, so divides. NH is a subgroup of G, so divides. So it's a Lagranges theorem. Okay, fine. The upcoming videos I will prove Sylow's theorem. I will prepare Sylow's theorem and prove 1, 2, 3.